As we discussed in several equation videos, the churn loss could be too high to get an open eye diagram at the receiver eye's input of chip B. Do you think this cross eye at the eye's input will work properly for clock recovery? You don't need to tell me your answer now, but check your answer at the end of our video. So, in this video, we will talk about why you need the phase transfer characteristic of Alexander band phase detector PD in a band CDR, such that we could tell if this cross eye will work for CDR or not easy. Since we discussed the Alexander PD in the Why band PD video, let's review the timing images and the target band PD transfer curve between the input phase error and average output voltage quickly. If you still have any questions about the operation in detail, please review the video. From the two A and B data samples and one edge sample T, we can tell if the clock is late when the T and B are the same, or T and A are different. Then the band PD output will be up to push the VCO to go faster to compensate for the late clock at the moment. Similarly, if the clock is early when the T and B are the same, or T and A are different, the band PD output will be down to slow down the VCO down to compensate for the earlier clock phase than the input phase. So, the phase detector was the heart of the CDR loop, which should provide the early day information or down-up controls to slow down or speed up the clock phase immediately. How do we verify the band PD efficiently? Think about the images of early day and clock rotations for 5 seconds. Correct. We just need to move the phases of the sampling clock together. Then, from the images of the clock phase earlier than the input data, the output of the band PD should be in the early region and pass to the late region, while the rising edge of the edge sample T pass the data transition. Then, the question is how to generate the clock phase shift respect to the input data. Think about the asynchronous images for 5 seconds. Bingo! Looking at the input data and sampling clock here, we could just make the frequency offset or peer offset between the clock and input data by a small amount of percentage. In this example, we make the data rate of the input data 1% slower than the clock frequency. Then, from the time domain waveform, the clock will phase shift to the original position of the input eye diagram after 100 times phase shifts. Similarly, from the phasor diagram, the clock phase starts at 0 degrees and will rotate back to 0 degrees after 100 times phase rotations. Therefore, after 1 UI phase shift over 360 degree phase rotation, the band PD output would have both early and late signals to indicate the clock was being earlier or later than the input data. What was the output of the early day you should expect? Here is a simple case study of the early day images from the clock phase rotation we mentioned in the previous slide. As you can see, the early day signals are only output large 1 and 0 if the clock phase was starting before the transition of the input data. And as long as the clock phase passes through the data transition, the early flag will stay 0, while the late flag will stay 1 at the most of the time, and vice versa. During this experiment, the functionality of the BBPD works well for sure. But what happens if the input I is closed? Obviously, the pattern of the early day is not clear to be differentiated now. Is this BBPD not working at all, since it cannot tell if the clock phase is earlier or later than the input data? Not exactly. Think about the BBP state size accumulation images of the decision for 5 seconds. Remember, the phase correction of the VCO has a finite BBP state size and cannot finish the whole phase adjustment in one decision. And it must be accumulated with several step sizes over a long time. Therefore, we still have another way of integrating the early or late decision to see how the early day response corresponding to the input phase error between the data and output clock, which is the phase transfer characteristic of Alexander PD shown here. But please be advised that the phase transfer is ideal, which does not match the cross eye here, and we will show it later. Before that, how do we get the phase transfer by integrating the early day signals? Think about a low pass filter images for 5 seconds. Exactly, a low pass filter would be a good integration up to a certain loop bandwidth. Usually, a 100 UI time constant should be good enough to filter out all the high frequency decisions in a row. Again, since the input I is closed, the early day signals are overlapped without identifying if the BBPD is working or not. Therefore, we could either take the early minus late or late minus early and pass it to a low pass filter with a 100 UI time constant. Then the output versus time over input phase error will match the early minus late or late minus early. Let's look at a simple case study with the original open eye and see what happened. Again, the input eye is wide open, and the BBPD can tell if the clock phase is earlier or later than the input data easy. Therefore, not only the output early day flag is very clear, but the BBP phase transfer is also very close to the ideal phase transfer, having an almost infinity PD gain around the 0 phase error and 0 in the early or late region. Okay, let's check what the phase transfer of a closed input I looks like. Think about a gain degradation image for 5 seconds. Yes, the gain of the BBP phase transfer dropped significantly, not just around the 0 phase error, but also at the early or late region. Therefore, it's more like a linear phase detector instead of the BBPD now. So, the input jitter will certainly smooth out the binary of the BBP characteristic significantly. Let's think about what impairment images could smooth out the phase transfer for 5 seconds. Correct. Without any circuit and input impairments, the phase transfer of the BBPD would be ideally nonlinear, as shown here one more time. But with any input jitter from the I side channel lossy media, other DJ source or random jitter RJ, the real band phase transfer would be smoothed out to be the real band PD1 here. Furthermore, adding any intrinsic impairments of the sampler inside the band PD, like the low input sensitivity, limited bandwidth, and high hysteresis will all contribute to the gain degradation further to be the real band PD2 as the cast images here. Therefore, we must run the band PD phase transfer functions in the SPICE netlist to capture all the impairments to avoid any design oversize, breaking the band PD's functionality. Here are the summarized images of why we need the phase transfer characteristic of Alexander, a band phase detector PD in a band CDR. To verify or design a band PD, the simplest way is to shift or rotate the phase of the output recovery clock regarding the input data by a small amount of frequency offset, for example 1%. Then the phase shifting in the time domain will shift back to the same I location after 100 times phase shifts, or the phase rotation in the phasor diagrams is back to the 0 degree phase after 100 times phase rotations regarding the phase of the input data. Then the early day signal shows clear regions while the output clock is earlier or later than the input data. However, the working case may require a wide open eye diagram at the first beginning. If the input eye of the data is closed, due to the eye size, the band PD might still work, but the early day signals are all over the place and we are not sure if that works or not. The only way of checking the band PD with a closed eye is to put all the early -day signals bits stream through a low-pass filter of 100 UI time constant to integrate over time. Then, the phase transfer characteristic of the band PD are generated. The first case study was the original clear early day region under wide open eye, such that the phase transfer is close to the ideal phase transfer of a band PD. Even though another closed eye did not provide a clear early day signal regions, the phase transfer was generated successfully with a degraded PD gain, which is okay due to the smoothing effect from the input jitter. Unfortunately, adding other impairments like the external DJ and RJ at the input and low input sensitivity, limited bandwidth, and high hysteresis of the sampler inside the band PD, the PD gain would degrade a lot. Therefore, running the band PD phase transfer function is the post layout SPICE netlist is a must. Capture the impacts of all the impairments to avoid any design oversize could break the band PD's functionalities. Thanks for watching. Before you go, if you are benefiting from those circuit images, I'd love to hear your feedback and place your comments down below. Lastly, please share the video link with the people who may be benefiting from it.